Today we'll discuss several applications where it is possible to do better than deep learning with simpler algorithms, or at least improve deep learning by ensembling deep learning models with simpler algorithms. I'll start by acknowledging how significant deep learning is. It has been a scientific and engineering breakthrough worth a Turing Award, of course, and one of the awardees is from Facebook, another one is from Google, another one is from a university in Canada. But aside from the science of deep learning, of course, what matters is the success in applications. And the success has been staggering in its breadth of topics and also in the quality of results. On the left, you see an example where a picture is interpreted by a deep learning system. It finds different kind of parts of the picture that can be labeled, and it creates a sentence that explains what's in the picture. So you have a combination of natural language generation here, image analysis, and putting things together. Another example here, also from Facebook, is real-time translation from French into English. The example on the right shows deep learning used to interpret the movements of fingers as a user interface in Oculus. And at the bottom, you see an illustration of a speech processing system. So it's hard to argue against deep learning. But if you look at what it takes to implement these solutions, it's very, very difficult and heavy on resources. There's a fairly old paper from Google suggesting that machine learning is a high-interest credit card of technical debt. And this is really why so many jobs exist for deep learning engineers, because there's a huge amount of infrastructure needed to develop this, and this infrastructure changes. So the code that was written in 2015, 16, it really doesn't work today for many reasons, including syntax changes, package upgrades, and so on. You have to choose your system, whether it's PyTorch or TensorFlow or Keras, and you have to optimize the models, right? And this takes huge amounts of power. So on top of these difficulties, it turns out that in some applications, deep learning doesn't really provide good solutions. So a fairly recent paper from September applies deep learning to a well-defined problem of predicting future configurations in the game of life. And the game of life, if you haven't heard, it's a fairly old invention of John Conway. You have a grid. In this grid, every cell is either alive or dead, and its status changes by deterministic rules in terms of whether neighboring cells are dead or alive. So if all the neighbors are alive, then the cell dies of, basically overpopulation, and if all the neighboring cells are dead, then the cell dies of boredom because there are no other live cells around. And so it turns out, depending on these rules, the system can develop long-term behavior of high sophistication. So the problem here that researchers asked deep learning to solve is predict the future of a configuration given deterministic rules. There is complete information here. It can be solved by very simple algorithms with very little memory used. It can also be solved by a convolutional neural net. And they did solve it with manually tuned weights. So basically, they found configurations where a CNN solution exists. Now the question is, can a CNN be trained on a large number of labeled examples, and you can generate as many as you want, and you start with random initial weights. So the surprising result was that training rarely finds good weights. Of course, you can be lucky, but on average and with high probability, it doesn't predict these future configurations very well. And the only thing that helps is upscaling the network, but then you're kind of brute forcing the problem. Okay, so now we have an example here, which is contrived, maybe not very practical, where deep learning is just not a good thing to use. And now we are gonna look for practical examples. But before we get there, let's review what it takes to deploy a successful application in production. The application needs to be computationally efficient. It needs to be robust in many ways, both software-wise and data-wise. Simplicity is very important, both for the implementation and for the dependencies, and of course also for the integration with other pieces. It has to be maintainable. Implementations are typically improved and incrementally modified. So it needs to be understandable. And working with a working DNN solution, even if it's reasonable, it may be undesirable because it's fragile, which happens in practice sometimes. There could be simpler methods, and also compute power can be a problem. Now, on top of these fairly obvious things, on the right, you see some additional concerns in terms of training. First of all, do you really have high quality training data? Do you need continuous labeling if the reality changes? Because in production, things can change. At Facebook, we pay a lot of attention to principles in newsfeed ranking. So the principles must be defensible. And if you can't explain what your DNN is doing, it's really difficult to get through, policy approvals. Another question is biases. It's known that black box systems have biases. So if you don't understand exactly what your system is doing, this could be a problem. Debugging, I'll give you examples where I was asked to work out a solution where some particular example wasn't evaluated correctly, and you have to be able to also apply your model to different contexts with maybe pre-post processing. Again, that may be easy or hard depending on the model. And so for DNNs, if you're comparing, people often tried DNNs and they didn't work. And so you just kind of say, okay, well, fine, let's try something else. But how do you make a conclusive comparison to have a negative result with a DNN? This takes time, and it's not, it's hard to justify it through management. But we have a couple of examples here which allow to make such comparisons. So in this talk, I'll discuss two important NLP applications with class imbalance. One class is much smaller than the other. The first application is narrow topic classification for text that is related to COVID-19. And the second one is clickbait classification. So we have competent solutions for in terms of deep learning. And the comparisons that we performed favor simpler solutions, either standalone or as add-ons through ensembling with deep learning. And then I'll try to draw some lessons. Now, I have to say that many examples here are simplified. The systems are a little bit more complicated that are in production, but this should be representative. So the first example for COVID-19 text classification, we have deployed classification in 64 languages from Amharic to Vietnamese, and this was mostly done by several people, 2 to 4. This is applied all across Facebook. URLs, Facebook search queries, Instagram hashtags, account names, page and group names, posts and comments. There are many integrity applications where there are hoaxes and all sorts of misinformation in terms of COVID, like what cures COVID. But the first application was whenever people do a search, and this started in February, we showed them the COVID Information Center that's shown on the right. And this is a fairly restrictive application, right? Being wrong is really painful here. So high precision is important, high recall less important. In other applications, it's the other way around. So in describing this problem, let me emphasize that there are short texts and there are long texts. For example, delimiters can be optional. You see a hashtag India fights COVID. We want to detect that, but tokenization here is difficult because you need to see that this is India fights and COVID, 3 different words. There are spell invariants, which you maybe haven't seen before, such as, Corona with K, with 2 R's, and so on. Sometimes people use zeros instead of O's. And there are emergent terms. For example, coronil is an Ayurvedic treatment that appeared in India. And, it doesn't appear in any dictionary. It didn't appear on the Wikipedia. So pre-trained models or embeddings wouldn't really, help here much. And if you want to learn more about integrity in social networks, there is a large fresh paper from Facebook describing this. So additional complications. The system needs to be integrated with SQL, Python, and PHP because, again, this classification is used all over Facebook. You need to perform real-time checking with low resource usage. Facebook was in a crunch in terms of resource consumption in the spring. People used, twice or more resources because they were online more. There are many false matches that you could detect, such as Corona Beer, Corona Extra. There's a city in the Philippines, Corona Dal. There's Coronado Beach in San Diego, and so on. So in 66 languages, if you wanted to train a conventional machine learning system, you need high quality data. you will not get this in, Armenian and Mongolian, at least not in time and not continuously updated. As I'll mention, things change, and you have to update your system to reflect the changes. Also, how do you check precision and recall of this classification? These are very challenging questions. So in terms of changes, we had several systems that Facebook trained in April, and in April there were protests against lockdowns, and so all the protests that were going on that were, in the news were against the lockdowns. But it turned out that some of the systems learned that whatever protests happen, they're related to COVID. And then 2 months later, or actually 1 month later, there were protests against police brutality, and some of these systems, fortunately, that didn't affect production, but they labeled erroneously, anti-brutality protests as COVID-related, which was wrong. So another issue is that different applications require different precision recall trade-offs. So you're built in one system, but it needs to be customizable. Should quarantine jokes be labeled as COVID-related? Not for search, not for the COVID Information Center, but perhaps for other purposes. And work from home is kind of a borderline case because this hashtag existed before. Of course, now it has a different meaning. And also in some languages, such as Bengali illustrated here, you have very unexpected effects where corona virasa means coronavirus, but if you swap these two words, it means don't get the virus. Fortunately, it's also related to COVID, as it turns out, but could have been worse. Now, here is the real deal breaker for how you build this model. So here, look at the dates. These are two titles from The Verge, and they describe what happened after a particular viral video showed up in May. It was called The Plandemic. It's basically a misinformation video by a former doctor. And this video went viral on all social networks, and it was quite unfortunate. Now, for the second installment of this video, some third-party researcher learned about this 1 day in advance, and he notified the community. So on some particular Monday, I got a call that we need to upgrade our system to account for this new video. And there were several very distinctive keywords there, so we did that. And also other social networks did that. And then the same person at The Verge now concluded that social networks managed successfully to stop this conspiracy video, right? So with labels, with training, you cannot do this in 2-3 hours. It's almost impossible. Now, what about the details? The solution, the scalable solution that we deployed is fairly old school. It's based on extensive use of regular expressions with big data. And the infrastructure here uses syntax common to SQL, Python, and PHP, which took some digging to define. With regular expressions, by the way, if you haven't heard of them, they're templates that capture large collections of different text variants. Right, for example, dot is any character, asterisk is any number of preceding characters, so dot asterisk matches everything. If you deploy such a system, you can quickly modify it, of course, but it quickly becomes unmanageable because regular expressions in one line they grow and they're hard to understand, hard to modify. So one of the first things I figured out was a platform-independent syntax illustrated on the right, how to create multi-line regular expressions. Now, each platform has its own way of supporting multi-line regular expressions. It turns out there is this clever trick with negative look ahead, which I'll not explain now, but it uses the syntax with question marks and exclamation marks, where you can create comments, and the line ends as comments are not really used, so you can create multi-line regular expressions this way. Okay, now at Facebook we have very quick deployment. We use a particular system at Facebook that can deploy very short pieces of configuration to all servers worldwide and make it available to all applications in pretty much all languages. So we now evaluate regexes and their changes with SQL queries on Facebook search queries. This was a very early, very powerful insight. This is important because search queries that people enter, they're full of keywords, and they also repeat. So you could see basically the most popular search queries of a kind, and you see examples here. So the two lists show the results of a change in the regular expression where you add some new matches, in this case corona news, with some misspellings in different countries and so on, also as hashtags. And on the right, we improved precision, so we don't match Corona beer anymore. We don't match Corona Dal, which is a city in the Philippines, and we don't match Corona beer and coronation and coronado and words like that. So now, how do we discover keywords? This is tough, right? In the example here, we started with just two keywords, COVID and coronavirus, which are used in many languages. And we went through French texts. We took everything that has COVID or coronavirus, and we see what else it has. And we sort these words by how often they appear. Okay, so here you immediately discover words that are related to the topic. For example, CAS, CS means case, right? A case of COVID. It's a very general word, so we call it a weak keyword, shown in red. Also, SARS is a weak keyword. You cannot use it by itself, but you can use it with other keywords. We also find a lot of spelling variants, MCOV, COVID, COVID with underscores, COVID-19, and we also find misspellings. Okay, and now the question is, so you find these keywords very quickly. How do you put them together into regular expressions? I would really love to have a full automated solution. Unfortunately, that doesn't seem possible. So we did as much automation as possible and as much human, thinking and intervention as necessary. We use, several features of regular expressions to compactly capture, spell invariants, such as character classes. So you could use C or K, A or O or zero. We use word boundaries for short keywords. We use zero width negative look ahead assertions to exclude, for example, Corona beer. So we can match Corona, but not followed by beer. Okay. And when we synthesize regexes, we also look for common phrases. And on the right, you see, for example, social distancing, which appeared early in the development of regexes, where there was the word social, there was the word distancing, but they're weak keywords. When they appear in a phrase, that's a strong phrase. And so we combine weak keywords and regexes for spelling variants into bipartite regex clauses, where in the middle you see this 0 to 80 quantifier for any character. And this question mark means optional. So it sounds like it's unnecessary because you could have 0 characters. But what this really means, it means lazy matching instead of the default Igor matching, which matches as few characters as possible, not as many. This helps speed, and this produces more explicable matches and also more matches. I'll talk about explicable matches a little later. But these regular expressions become big, and so we distill them by the following piece of code. It's about 50, 60 lines of code. So what it does, it splits the regex into chunks and keywords, and on the right you see a list of those. And for each chunk and keyword, it blanks out all copies of this chunk or keyword in the regex, and then it evaluates the recall drop for the regex. And you sort the chunks and keywords by how valuable they were by this percentage drop. And so 0 to 80 was important because it's used in many times. But then you see the second one was virus and infection. These are really useful, so we don't want to delete them. But some keywords, for example, epidemic doesn't seem very useful because whenever it's used, also something else is used. So it appears close to the end of the list. And by shrinking these regexes, we also can improve the matching time, which is important at the big data scale. And the timings here, if you know the timings for your deep learning system, you could see that this is much faster than what deep learning can give you. This entire approach supports explicability, customization. We optimize regular expressions for clear matched snippets. For example, when we match Corona, we also match virus if possible as an optional match. It's not necessary to get the correct result, but it's helpful when you look at the match, because then you look at what matched and you could see that 2 pages of text matched correctly because of what's matched. Otherwise, you have to read the entire text. So this helps a lot when evaluating results. And this also supports black box processing, post-processing, where some matches, such as work from home, may be discounted, right? And you could have another layer, potentially using some additional machine learning tools. It can basically, post-process and change the decisions. In this case, vaping epidemic was a false match, and we intercepted that. But of course, we can also modify the regex. Okay. Now, label data can be used. It's not necessary, but we had a DNN trained, and this helps finding missing keywords if you do have missing keywords. Keywords that are too general, and also for N-level word grabs. Here's an example where the DNN trained in Russian was run in August, and the phrases that it finds are actually related to protests against, fraudulent elections in August in Belarus. And so again, this is not correct, but we can interpret these things and we can decide whether our regexes need to be modified. Now, for keyword discovery, let me maybe repeat what I said earlier, that by looking at the matches, we can discover more keywords. We could do this at the level of whole documents. We can also do this at the level of matched snippets. So if you match corona and then virus and there's something in between, this something in between has a high likelihood of being useful. And when you rank these things and show it to a person can decide. Here's a comparison to DNN. There is a lot of data here. We sampled 300 posts in English, and we labeled them using, so these included positives by DNN and by regex, right? So the coverage was pretty good. And we performed manual evaluation of each post. And you see that accuracy is reasonably high because the prevalence is low. It's a class imbalance problem. We have tier 1, tier 2 regexes. Tier 1 is higher precision. So you see precision is 98, 99%. And this is only for English, but carries over to most other languages. Tier 2 has much higher recall, and it's available for fewer languages, but more than 10, and these are high use languages. So you see that the regexes improve in both precision and recall upon the ML classifier, which is pretty interesting, right? Given that this is a much simpler technology, it's much faster, much more lightweight. And I had some examples here of false positives for the DNN classifier. Basically, there's a lot of temporal overfitting where the DNN classifier fits something to the data and then the data changes. Whereas regular expressions, they encode our understanding of the language and how general the words are. Now, the evaluation, of course, we didn't perform manual evaluation for 66 languages. We have some automation here. So unlike entire posts, unlike entire, pages of text, short match snippets repeat. And these snippets we may repeat more than others. So we rank them by how often they repeat. And basically, we build a short, safe regex. Here's an example for Arabic. For most languages, 3 to 15% of matched posts must be checked. They were not caught by the safe regex, but the safe regexes essentially confirm the correctness of matches in most of the cases. Okay, and this automation is very impactful in practice. For the 3 to 15%, you can use automated translation, but the text needs to be long enough. Okay, so the manual languages for English that we performed earlier validated this methodology, and we used it for other languages as well. To summarize, narrow topic classification for regexes, it's very efficient in terms of performance. It's quick to revise. The software is self-contained, very interoperable with other systems. It's robust to changes in data. It handles word forms, misspellings, contain individual keywords and phrases, and it captures exponentially many keyword combinations, which would be difficult. If your deep learning system uses embeddings pre-computed for words from the Wikipedia, you already lost. You have to use emerging keywords. We use exclusions with negative look around, which is a fairly nifty feature in regular expressions. We provide explanations for every match, and there is both white box and black box customization. And for DNNs, unfortunately, many of these things are not available. DNNs handle synonyms and similar words, and transfer learning is possible, but this takes time. And if two different synonyms repeat, you could definitely code them into a regex. Okay, now let me transition to the second example. So this is a little trickier. This is clickbait classification, and there are two types of clickbait that we distinguish at Facebook: exaggeration and withholding. So clickbait in general is a title which withholds some information or exaggerates some information that makes you want to click, and then you're disappointed because it's just not there. It's not what it looked like. Now, there are detailed guidelines, and the guidelines we use are more nuanced than those in Kaggle contests. We also support 20 plus languages versus just English and Kaggle, and we do have large sets of labeled data. So this is kind of a more favorable context for deep learning systems. And the one we have for this comparison is a ByGru architecture, which is similar to a Kaggle winner. It's improved in many ways. It uses additional features, whereas the Kaggle winner was featureless. It just used word embeddings. And so, you know, this is a simple model, single model that uses multilingual embeddings, whereas we build separate models, not regular expressions, for different languages. Now, unlike regular expressions, keywords here are risky because the same keyword may participate in a clickbaity title or not. It's really the style of the title, not the contents, okay? And also there is a lot of subtlety. There are different scores of clickbaitiness. So just a yes or no classification is not good enough, okay? Now, we do some problem analysis here, and you figure out that word ordering is not that important for clickbait because it's hard to find two examples of titles that essentially have the same words, but in different order, but different clickbait status. Okay, word adjacency is helpful, a little helpful, but it can be captured by word n-grams. So basically, you can use a bag of word n-grams. Clickbait detection doesn't really require understanding, you know, the semantics of the word. So pre-computed embeddings are, you know, questionable necessity, and also it's a shallow problem in the sense that the clickbait, well, the titles that we're working with are typically less than 20 words per title, and the median is 9 to 10 depending on the language. So there aren't, you know, subtle long-range word dependencies. This is what deep learning is good for, at least some architectures, but you know the problem is simpler. Now, what is important is character level features, and some of the deep learning models that we've seen, they have difficulty combining word level features with character level features. Character level features are important because there are many word forms in most European languages, and there are languages with optional spaces such as the Burmese and Sinhalese languages. And also when you deal with 20 plus languages, this is important. The available NLP techniques such as stemming, they're limited. You don't have stemming for, you know, Burmese and some other languages. So we want a generic solution, and we built a lightweight classifier that uses word and character level n-grams. It uses a very simple TF-IDF factorization. There have been some studies recently showing that TF-IDF actually is surprisingly good for some classification tasks because it can give you very high dimensionality. Trained embeddings are usually 200 to 300 dimensions. TF-IDF can be 1 million or more. We get away with 100 to 1 million. 100K to 1 million. And we also use powerful features, including stateful features.
Just sorry, Igor. Just
Hello?
We're 5 minutes over.
Okay, I see. I'll wrap it up. So basically, the comparison. I'll just show you the comparison, and you know, the lightweight system improves upon the ByGru, and this happens in a lot of different languages. But the best results are for ensembling, where you combine in a very simple way the ByGru and the logistic regression based on these features. So I didn't tell you about the you know, nifty features that we developed, but that's one of the reasons why it works so well. So we have some lessons, right? Deep learning may be a hammer, but not everything is a nail. And lightweight classifiers for problems that are simple enough to give you fast development cycle, relatively easy tuning, much lighter computation, and explicable results. And that's it. Thank you.
Thank you, Igor. Yeah, unfortunately, we don't have time for questions, but thank you so much for your presentation, and I'll turn it over to Shiva to introduce our next presenter.